Carbon dioxide is very effective for miscible displacement of oil and formations. In most cases, carbon dioxide achieves miscibility with reservoir oil by extracting light to intermediate components of the oil in a multiple contact miscibility vaporizing gas drive mechanism. In addition, carbon dioxide improves oil recovery by swelling in the oil, thereby reducing its viscosity and lowering interfacial tension between the oil and the CO2 enriched fluid. Of course, there's the downside of extensive corrosion. So this has to be planned for in CO2 EOR projects. That said, these projects are quite attractive because of the positive impact on the environment. So oil and gas reservoirs with good geological seals could serve as for storage of carbon dioxide, and this is actually driving CO2 EOR projects in different parts of the world. So this just to reiterate what was mentioned before, that CO2 is effective for recovery of oil. One, because CO2 is very soluble in crude oils at reservoir pressures, and thus it swells in the net volume of the oil, reduces viscosity, even before miscibility is achieved. And on achieving miscibility, both the oil phase and the CO2 phase, which contain many of the oil's intermediate components, can flow together because of low interfacial tension and the relative increase in the total volume of the phases compared to water. So therefore, at higher temperatures, higher pressures are needed to increase the CO2 density and, of course, to achieve miscibility. So CO2 is actually is a tested method. It's not has been tested and found to work for in improving oil recovery in different parts of the world. So let me talk of strategies used in effectively flooding reservoirs with gases. So mobility control is a major concern in miscible gas injection processes because of the relatively low viscosity of the injected gas. Of course, this will result in a very unfavorable mobility ratio between the injected gas and the based oil. This causes viscous fingering, which creates low volumetric super efficiency. To remedy this condition, most miscible gas injection processes are actually done in conjunction or simultaneously with, are done in conjunction with water to improve the volumetric sweep. So if water and gas are injected in an alternating cycles, the process is referred to as water alternating gas, that's WAG. In some applications, it's not done in alternating cycles, both are injected simultaneously, and this is referred to as simultaneous water and gas flooding. So swag injection strategy is considered to be a variant of the WAG. So the water alternating gas injection strategy is used in most miscible floods around the world with a ratio of 1:1, that's a per volume of 1 per volume of water to 1 per volume of gas, being the typical ratio. So you should also note that the application of the water alternating gas results in loss of injectivity over time. So most municipal gas floods are initiated with the continuous gas injection. So typically what is done is, first of all, it will be gas injection, let's say CO2 injection, and then it is switched to either the water alternating gas or the simultaneous water alternating gas strategy for better mobility control. The volume of gas injected can now be reduced as the flood progresses to reduce the cost and to improve mobility. This injection strategy is described as tapering. So as it's used in most CO2 and hydrocarbon injection projects to reduce the cost of injecting gases into the reservoir for hydrocarbon recovery. So let me go into chemical enhanced oil recovery. So in chemical flooding, the primary goal is to recover more oil by either one or combination of the following processes. So one, to achieve mobility control by adding polymers. By adding polymers, you will now reduce the mobility of the injecting water, and reduce interfacial tension using surfactants and or alkalis. So therefore, these methods will require conditions for favorable water injection. I see here that what we're trying to do is to make the water flooding process more effective. So hence, chemical flooding is used for oils that are more viscous than those that will typically be recovered using gas injection methods, but less viscous than those which will require thermal methods. Chemical flooding processes are displacement processes that improve oil recovery from reservoirs with the aid of chemicals that are generally called surfactants, polymers, and alkalis. These chemicals are combined in various proportions to create injection systems, which are referred to as polymer surfactant. These are micellar processes, and alkali surfactant polymer, that's ASP processes. All of these methods involve mixing chemicals in water prior to injection. And this just shows a schematic of the process. If you follow the flood front from the injection well to the producer well, you see that number one, you have the oil zone. Two, you have the surfactant ahead of the polymer solution, which is ahead of some dry water. And then here, of course, these are surface facilities. Basically, this is for mixing surfactant on the surface, for injecting the fluids or the chemical flood into the reservoir, and this for production. So this just highlights some considerations for chemical flooding. Reservoir permeabilities for chemical flood conditions need to be higher than those for gas injection methods, but not necessarily as high for thermal methods, since lower mobility fluids are usually injected in chemical floods. Adequate injectivity is required. If the reservoir was previously water flooded, the chemical flood candidate should have responded favorably by developing an oil bank. Generally, active water drive reservoirs should be avoided because of potentially low remaining oil saturations. This takes you back to the conventional screening guide lookup tables. So in selecting the chemical flood method, you need to ensure that you have sufficient residual oil saturation in place. Reservoirs with gas caps are ordinarily avoided because the oil could resaturate the gas cap. Formations with high clay contents are also undesirable because the clays could absorb the injected chemicals. In most cases, reservoir brines of moderate salinity with low amounts of divalent ions are preferred, since high concentrations interact unfavorably with chemicals. And one of the most successful methods around the world is the low salinity water flooding, which I end with at the end of the presentation. So for micellar floods, that's for polymer surfactant floods, a slug of the micellar solution, the slug is a solution which consists of water, the surfactants, electrolytes is injected into the reservoir. The size of the micellar slug can vary from 30% to 3 to 30% of the pore volume, depending on the flood design. The slug is now followed by a buffer solution made up of polymer and water. And this is chased by dry water. You know, we saw this in the schematic earlier. The polymer solution sometimes contains a biocide to control microorganisms which could degrade the polymer, thus reducing the viscosity of the flood. And of course, that will result in unfavorable mobility ratios. The micellar slug is formulated such that a favorable mobility ratio will exist between the slug and the oil bank formed during the flooding process. Adsorption of surfactants on the rock surfaces can be reduced by flushing the flood zone with fresh water. And this, the intricacies of the flood. Micellar floods are on the decline because of the cost of the injectants and limited economics success of field test trials around the world. For the, in this slide, I'm just highlighting two of the polymers. You have the hydrolyzed polyacrylamides, and then you have the xanthan gum. This is just giving some details to the nature of the polymers, of some of the polymers that are used in the process. For the alkali surfactants, so compared to the micellar flooding, which discussed earlier, the alkali surfactant polymer flooding is more widely used. It utilizes a favorable mechanism of key components, the alkali, surfactant, and polymer to improve oil recovery. The main functions of the alkali component is to promote emulsification of the crude oil, reduce interfacial tension, reduce adsorption of the surfactants on the rock, and to regulate phase behavior of the mixtures. The main function of the surfactants is to reduce interfacial potential, that has been discussed before, while the polymers are for mobility control and to improve sweep efficiencies. The alkali surfactant polymer is tested and proven both in laboratory and field tests. And it's applicable to sandstone reservoirs with at least pilot tests to suggest that it could also work for carbonate reservoirs. For polymer flooding, basically similar to what we discussed before, but this is just highlighting, this is only the polymer is employed here, of course, to reduce the mobility of the water flood and for better sweep efficiency. Factors affecting the application of the polymer flood are the cost of the polymers, permeability of the reservoir, and temperature of the reservoir. The cost of the polymers, of course, limits the concentration that could be used. And of course, polymers are generally not stable at temperatures higher than 175 degrees Fahrenheit. Of course, this will need to be checked out in the light of recent research, you know. Okay, let me talk a little bit about microbial enhanced oil recovery. So microbial activities in the reservoir are believed to increase oil recovery by altering the wettability of the rock, reducing interfacial tension, reducing oil viscosity, and generating gases such as CO2 and production of surfactants also. These mechanisms which combine to which in combination lead to oil recovery are quite complex and are still being studied. Generally, The microbial enhanced oil recovery processes are applicable to reservoirs with salinities as high as 150,000 parts per million, viscosities in the range of 5 to 50 cp, and reservoir temperatures as high as 176 degrees Fahrenheit, porosity as high as 20%, rock permeabilities at least as high as 50 millidarcies and that depth. And they have been used in sandstone reservoirs. So the bacterial sources could be indigenous or could be exogenous. Indigenous refers to bacteria already present in the reservoir, while exogenous are those cultivated and injected into the reservoir. Also, the microbial process could be aerobic or anaerobic. For aerobic processes, it requires injecting oxygen to maintain the bacterial concentration. And of course, injection of oxygen would lead to more corrosive tendencies. On the flip side, anaerobic processes would require injecting nutrients to sustain bacterial growth. And of course, it has its cost implications. So 47 microbial flooding recovery field tests have been carried out in China. I think China is more of the test bed for this technology. And then the Darkwing Gulf field has notable for a number of projects. And then recoveries as high as close to 5% of the original oil in place have been achieved with a slug size of less than 10% of the pore volume. Of course, there are still challenges with chemical EOR, issues with surfactant injection, especially at high salinity and high temperature. Even though the alkalis are cheap, but they could lead to other operational issues like scaling, emulsions, and plugging. And then nearly all polymer floods have been implemented in sandstone, so there's still the issue with carbonates. And then they are not particularly suited for light oil reservoirs. This view graph just shows areas for current research. You see that for the Darkwing oil field, you see that the ppm is less than 10,000 parts per million, while temperatures are less than 160 degrees Fahrenheit. And as you begin to go outside this envelope, this is the zone where the application of chemical EOR, whether it's a polymer or microbial, gets more challenging. So let's go into thermal EOR. So for thermal EOR processes, they require supply of heat to the rock and fluids, thereby enhancing the ability of the viscous fluid to flow due to reduced viscosity. And of course, that will lead to flow into nearby production wells. Steam injection and in-situ combustion are the most popular methods. Steam flooding has achieved substantial commercial success around the world and is ranked as one of the top EOR processes. In-situ combustion, on the other hand, has attained limited commercial success and has been applied in few reservoirs around the world. The major problem with in-situ combustion is the ability to manage and control the advancement and progression of the combustion process. I'll still talk about these two combustion in a short while. So the three main steam flooding methods are cyclic steam stimulation, steam drive, and then the steam assisted gravity drainage. You can look at the steam-assisted gravity drainage as a modification of the steam drive, which is typically applicable to very heavy oil reservoirs, including tar sands. In-situ combustion requires the injection of air where air downhole, and then the oil is ignited, heat is generated, the gases are there's combustion of the gases, and then a recovery is enhanced. So let's just look at the methods briefly. Cyclic steam simulation is a simple and cheap method of applying thermal recovery processes, of applying thermal recovery on a reservoir. It involves injecting steam into a well for several weeks, shutting the well in to allow for the steam to heat the oil in areas around where the steam is injected, and then the well is put back in production to recover the heated oil. This process is repeated when the production from the well declines to a low level. So the cycle is repeated many times until the ratio of the oil produced to the steam injected, which is termed the oil-steam ratio, drops to levels that are considered uneconomic. If you take a look at figure TE1, so this is the cyclic steam stimulation is usually in three processes. First process is to inject steam into the reservoir, and then you allow the steam to condense, the oil and the rocks to soak up the heat, and then when you now start having some mobile oil, it's produced to the surface. In some books is referred to as the huff and puff process. Steam cyclic stimulation was the first steam flooding technique used for heavy oil reservoirs. Still used in limited cases. It's still used as like a pilot test to see whether steam injection is a viable EOR method before you undertake more extensive pattern methods, since you could do that with a well, as compared to some of the other methods which require more extensive equipment. The next method is the steam drive. So in the steam drive, steam is injected continuously at injectors with the aim of driving oil towards producers, and you could easily visualize this from our discussion on water flooding. Typically, in most projects, steam injection is organized in patterns. For instance, for the normal 5-spot pattern, the producer is in the middle and surrounded by 4 steam injectors. The experimental and field evidence has shown that the mechanism of recovery for steam drive is dominated by gas drainage, caused by steam rising towards the top of the formation due to gravity override. And if you look at figure TE, you see this is the process that is the progression that is expected for the flood front. You see steam injected, of course, you'll have hot water due to condensation, and this looks similar to what we had for the miscible flood. However, this is what tends to develop. So you have the steam rising to the top of the oil, and this is what's referred to as gravity override. So you see that this tends to affect the sweep. And of course, this will lead to early steam breakthrough at the producing well. The accumulation of the steam at the top of the formation creates a steam zone which continues to expand with more steam injection. This steam zone can propagate and break through at the producers to cause inefficient utilization of the energy from the steam due to cycling. The main challenges of managing a steam drive project are monitoring the size and growth of the steam zone, monitoring producers for early steam breakthrough, adjusting steam injection rates, and measuring the trend of oil-steam ratio for each pattern. And of course, you could evaluate this via reservoir simulation prior to embarking on even pilot projects. The third steam flooding, steam injection method is the steam assisted gravity drainage. It's applicable to heavy oils, oil sands, and being used in China, Venezuela, and Russia. So it involves the use of two horizontal wells about 15 feet apart, located close to the bottom of the formation. So it's such that a well will lie above the others. Steam is injected into the top horizontal well, and the well below it functions as the producer. So the steam creates an expanding steam chamber around the injectors as more steam is injected. So within the steam chamber and its boundaries, as the viscosity of the oil is reduced, of course, the oil becomes mobile and it drains towards the producing well. This process should be applied for reservoirs with thickness greater than 50 feet, good vertical permeability, and with no thief zones. In some steam assisted gravity drainage projects, a hydrocarbon solvent like methane is added to improve recovery. This variant is referred to as expanding solvent steam assisted gravity drainage. And there's also another variant. So figure TE3 shows the typical process. So you see the producer is below, the injector is just above, that's what they said, 15 to 25 feet. And of course, from the steam injected, you have a steam chamber, it expands, and then oil becomes mobile and drains towards the producer. This is a variant referred to as cross steam assisted gravity drainage method. In this case, rather than having the injector being a horizontal well, you are having vertical steam injectors. Oil recoveries from this process in pilot tests reach up to 65% of the oil in place in the project area compared to cyclic steam stimulation, which achieves just in the range of 25 to 30% of the initial oil recovered. This is a schematic which is further underscoring or further illustrating the steam assisted gravity drainage. So you see, this is the conventional thing. So this is just highlighting, so this is the steam chamber. You see you have heated oil falling, you have rising steam, and of course comes to the producer, and then you have oil coming to the surface. Water alternating gas was described earlier as a strategy for gas flows to reduce viscous fingering, improve sweep, and recovery. This concept can also be used for steam floods by injecting water alternating with steam to reduce steam fingering and to improve vertical sweep efficiency. In this case, where you're having water alternating steam process. The main benefit of this process is over continuous steam injection is the reduction or elimination of premature steam breakthrough at producing wells. So because early steam breakthrough would lead to wastage of the heat energy and also low productivity of oil. So as regards the management of steam flood projects, there are, of course, there are a number of challenges. So in managing the steam projects, you could look at it from the surface equipment management perspective, well management, and reservoir management. So the key objective for surface equipment management in steam floods is to minimize heat losses and optimize the process of generating steam. So two things are key here. One is proper insulation of tubing and joints to minimize heat losses, and then incorporating cogeneration of steam and power as an effective means of improving the economics of the project. As regards well management, of course, the typical steam flood consists of injectors, producers, and some cases observation wells. In this case, you're not just observing pressure, you're observing temperature. Management of steam injectors usually requires profile control so that steam can reach the targeted intervals. This is achieved by using surfactants or high temperature polymers to reduce the mobility of steam or redirect the steam to the right to accept intervals. Another practice is the use of multi-zone completion techniques. So the focus here is to ensure that the steam chamber is created at the targeted intervals so that the thermal energy works in such a way that the oil becomes mobile and gets to the producers. As regards the reservoir management strategy, this is what is highlighted here is the use of observation wells to monitor temperature and the growth of the steam zone. So this can be accomplished by running temperature surveys and or equipping the observation wells with fiber optic distributor temperature sensing equipment. Steam flooded reservoirs require high levels of monitoring and surveillance due to the close spacing between the injectors and the producers. So the recommended practice is to manage the steam flooding process with a numerical thermal simulator with the goal of optimal utilization of heat energy from steam. For in situ combustion or high pressure air injection, this entails injecting compressed air for in situ combustion into heavy oil reservoirs, for high pressure air injection into light oil reservoirs. So gases such as oxygen are injected so that it contacts with and then they are combusted. So the high temperatures will now create a combustion front. The difference between these two methods is blurry, but they are actually well defined. As I mentioned earlier, the in situ combustion is associated with high peak temperatures, 350 degrees centigrade to 600, and you might require ignition. But for the high pressure air injection process, you may not have the peak temperature and doesn't require any ignition for it to occur. In situ combustion appears to be more applicable to heavy oil reservoirs, while high pressure air injection is suited for light reservoirs. Both are termed as air injection processes, and so if you look at this is your injection well, and remember it's air that you are injecting, and then you'll have this the mobile bank, this condensation zone, coke zone. This is the evidence of combustion zone, and then this is the bond zone. So so the displacement part consists of an air zone behind the combustion or reaction zone. The combustion zone is preceded by choke zone, condensation zone, and immobile bank. High oil recoveries have been reported from laboratory and field tests of air injection process. However, there are few air injection projects around the world. In the US, most of these projects are located in North and South Dakota. Steam flooding processes are preferred to air injection processes, even though both have similar training criteria. This is the result of air injection being considered a more risky. The air injection processes are more difficult to control as compared to the steam flooding processes. So what are the considerations for implementing EOR projects? So taking an enhanced oil recovery project from initial screening to fluid implementation is a long, labor-intensive process. It's one of the most elaborate processes in project management and execution, and requires all areas of petroleum engineering. Dare say not just petroleum engineering, but also other engineering fields. So enhanced oil recovery projects require input from all these professionals, including facilities engineers and economists, for proper evaluation of the process. The procedure for screening, testing, and implementing is divided into stages that you see. The first thing is screening, a selection of EOR methods that can be adopted, quick economic evaluation of selected processes, then geologic and reservoir modeling of the selected processes. Okay, basically modeling of the reservoirs, and then simulation of the EOR displacement processes, recovery processes, and then you do a more expansive economic evaluation process. Then pilot testing. This is very important, especially for unproven technologies. So based on the results from the pilot test, a pilot test is basically usually something a little more than just a laboratory experiment, but not as extensive as a full field deployment. Of course, it's basically a thing of scale. And then with more updated simulation models, you can do more detailed economic evaluation, and then you do a field implementation, and the project is managed. So the total cost and the breakdown between the investment in the EOR project depends on several factors. So are you going to require new installations? Do you require new wells? What's the time frame for this project? So it can be assumed that EOR methods such as CO2 EOR and low salinity injection are the most capital intensive, while the chemical methods have very high operating costs, of course, due to the injectant cost, whether it's the polymers, surfactants, or the other chemicals. In your free time, you can look at the BP-operated Clare Ridge field, which came on stream in 2018. This is the low salinity water flooding was employed, and is estimated to have a breakthrough price of $3 per barrel. This is even cheaper than our own development costs, which is still for conventional development. So in conclusion, realization of the enhanced oil recovery potential can only be achieved through long-term commitments, both in capital and human resources. I know what will come to mind is in the light of of developing sustainable development programs, what's the place of enhanced oil recovery? I think you saw it in one of the earlier slides that as of 2018, it contributed basically 2%, you know. So it could still support um, some economies, and could serve as for shortfall for when energy demand is high and you don't have sufficient supply, So this is my overview on enhanced oil recovery processes.